Okay, so I'm Krister Walfridsson, and I'm going to talk a bit about C now, how to avoid buffer overflows and other undefined behaviors. So the way we are going to do this is doing formal verification. So there are a lot of myths about formal verification when you search for that on the internet. So I thought it could be fun to just show an example how we can prove that our program doesn't have these kind of problems. So the general idea here is to add assertions that detect all bad things we want to prevent. Then we'll prove for each assertion that the condition always is true. And, well, two things does not happen, so yeah, we know that our program doesn't have these problems. So the more assertions we add, the more sure we can be that our program does exactly what we want. So you have a trade-off here. If you are only interested in that it returns 5, you just add an assert for that, and then probably quite easy to prove, but you can add more and more as need arises. So unfortunately, we have very little time, so I'm going to use a toy program. A sorting function, this is normal insertion sort. I don't know if the text is too small here. We will zoom in later, but all of you know how to write an insertion sort, so it's just two nested loops and a swap in the middle. I split this in 3 functions. That's not needed for the verification. It's more for pedagogical reasons, so I can point out one thing at a time when I prove stuff. So the tool we are going to use is frame as C. So when you load the source code in the GUI, it looks something like this. So frame as C is a framework for analyzers for C. So on the left side, you have a panel with the different plugins you can use. You can configure them, set times out, and that kind of thing. On the right side, you see the code we are trying to prove. The middle one is sort of the most important for now. There we have the source code as the tool sees it. So it runs the preprocessor. It has removed syntactical sugar. So you can see here that our 4 loops have been changed to while loops were initialization before it. In this view, we will also see things that the various plugin adds during the process. Finally, in the bottom pane that we will not use, there you can actually inspect how the tool is reasoning about the code. So to run frame as C, you just run it like this. You can either do it on the command line or on the GUI. So the WP, that is the plugin we are going to use, the weakest precondition thing. It's the plugin that actually do formal verification. The next option with the RTE, it tells the tool to add assertions for that detect runtime exceptions. That is what usually the term used in the formal verification world for things that should not happen at runtime, like division by 0 and this kind of memory buffer overflows and that kind of thing. So if you look at GUI now when we have run this, we see these blue lines where it has added assertions. And you see for now we focus on the yellow dots. That is the status of how the tool has managed to prove our program. So it's yellow, it means essentially it has given up. If it's red, it has found a bug. If it's green, the assertion cannot trigger. So if we zoom in on one of the functions here. So let's start with the swap. So we see here that the tool has added 1 assertion for each memory access. it does not add normal as such because, well, we need to check things that you cannot check in C. So FrameC has its own language here that's added in comments, comments starting with the @ sign. So it's using that valid P. That means that P points to valid memory for read and write for that type, or valid read, that is, doesn't need to be writable, but otherwise valid. So yeah, everything is yellow here. It doesn't know anything. And the reason is that, well, the function is probably what we would write as such, but it's up to the caller to not call it with bad data. And I guess most of you is aware of, sort of, at least, programming by contracts. The thinking there is that when you have an API, you have a contract between the caller and the function. So there are some preconditions that must be fulfilled before you call a function. If those are not fulfilled, it is a bug in the caller, not in actually our function. Then our function will do some work, and it promises to actually do certain work. And the caller doesn't need to check that the work actually has been done. So here we need to add our contract, so the tool knows what to check, essentially. So if you take a class in form of verification, you usually do this waterfall style. You think, oh, I have a problem, I should sort. And then you start to write a contract what sorting does. Then you write your function, then you verify it. Here we go a little bit backward. We just add enough contracts so we can ensure that all our assertions are proved. So in most cases, it is fine to just add the preconditions. So in our case here, we add these requires statements. So what we say here is that this function requires that we get a pointer, 2 pointers that point at valid memories for read and write for any integers. So when we now run the tool is that, okay, we are sure that this function, provided it gets the right data, it will never cause any problem. The required statements are yellow here. That means that we have some calls somewhere that the tool doesn't know if it always give it valid data or not. So let's continue with next function. So we have this min index. It returns the minimum, the index for the minimum elements in the range from start index to n. And we see that it has 4 assert statements added by the RTE thing, so 2 for memory and 2 for signed integer wrapping. One thing to note here is that in FrameC, within its assertion language, it's using big int. So that is why we can do the wrapping check by just adding and checking for a large number rather than the more annoying thing you usually need to do in C. So in the same way as previous versions, previous function, we add some requirements. So we know that start index must be in the range, otherwise this function is meaningless. And in this case, we must have valid memory for reading in the range that has this syntax where you take a pointer plus a range. Unfortunately, that does not really help us proving this function. The problem here is that FrameC is rather bad at reasoning about loops Or rather, it is decent at reasoning about loops, but in principle, how these tools work is that they take all the information they have, then try to combine it in various ways until it comes to the statement it wants to prove, and you can see that they are the same, essentially. And loops is too much information to do this kind of thing. So we need to help it a bit. The idea here is that we add some new assert statement, or, well, actually slightly different syntax, but that prove true but simpler things that the tool then can use as a stepping stone to prove the other stuff. So there are three things we need to say. One is the loop variant. That is a value that should decrease for each iteration in the loop. The tool is using that to ensure that we don't have infinite loops and that kind of thing. And it is nearly always n minus I, which is a bit stupid because the tool could add it itself. Because it will prove that this is true. So even if it added something and it wasn't true, it could then tell us that, oh, you need to add something here. And more mature tools usually do this, but FrameIC, we need to add that itself. Similar for the loop assigns, where we need to tell it which variables that are modified in the loop and used outside of the loop. In this case, we see that I is not really used outside of the loop. But if we look at, well, the middle pane without syntactic sugar, we have an initialization and a while loop. That is why we need to have it here. And finally, we need to have an invariant statement. That is something that is true before and after each iteration of a loop. So that is the hardest stuff in doing this kind of verification, but you get a feeling for a while how to reason. So in this case, we know that the min I and I are in range all the time. Well, the last one will actually be n rather than n minus 1. Anyway, this is enough that the tool will verify that all assertions are okay, and also it verifies that all the new loop stuff we have said actually is true. So we cannot introduce problems by lying here. So finally, we should finish the proof that this sort is okay. So again, we start by adding the same kind of information as we had done in the other two functions. Rather straightforward, we have, it will be meaningless to actually have a negative n here. The function sort of will not cause any problem, but it will be really bad if someone called it with -5 or something. So we say that we always must have at least 0 elements, and we must have a valid pointer with the range. And the loop in the same way. Here we just say that we have the iteration variable is our loop invariant. But that doesn't help us too much. The thing happening here is that we are calling functions. When the plugin tries to reason about what happened in the functions, it only looks at the contracts. And our contracts doesn't say anything about memory accesses of the functions. And for safety, the tool then assumes it will write sort all over the place. So we need to add more information to our contracts. So the min index is sort of easy. It doesn't write any memory at all. So we say assigns nothing. Again, we need to check the proof for this function, so we didn't lie in our contract, but it verifies that, yeah, it was correct. It doesn't assign anything. In the swap function, it writes to the pointers. So we say that it assigns to each of them. And again, this proof still works. So that's fine. And we need to update the sort now, because now we are saying that it's actually writing to our pointer in this range. So we need to add that to the loop. And I also add that to the contract, because otherwise no one would be able to call it anyway. So, but no progress. The problem here now is that if you look at the swap function, the second argument there is p plus I min. And the tool has no clue what I min can have, what value that can have. So again, we need to add that to the contract here in min index that returns min I. And our intention is that it must be in range. So we add that as our post condition. And again, look at the proof. And now the tool sees that, yes, we are right. It cannot fail in any way. And now it managed to prove our full function. There are some blue circles on the top in the requires, and that's only a notification that we actually have new callers of this function. So the main reason why difference that from the normal case is that it is possible to actually do a contract that can never be fulfilled, and we will need an extra test here to actually call it to see that if we are building a library that we have not made such a contract. But otherwise, we know that we have made a function that fulfill all the contracts and all the assertions within it. So we could go on here and add more things, actually verifying that it has sorted the data, that the return data actually is the same element that was input, but in a different order. That is actually not much harder than what I have showed already, but I don't really have time to do it. But the principle here, for example, you do an expression of what it means to be sorted, and you put an invariant that the first I element are sorted for each iteration. And you need to update the other two functions to say, well, the swap, that it actually is copying data from one place to the other. And then everything works out. So do the fully verified function is sort of adding 5-6 lines to it. If you have predicates that express what it means to be sorted and the permutation. So this has been a rather annoying and time-consuming thing to do. But I could argue that, well, if you were going to do this kind of assurance in other ways, it will be as time-consuming and annoying. And a good thing with the proof here is that if you start modifying the code in any way, the tool will complain until you have convinced it that you have not introduced a new bug. The thing I have done here, it was a toy example, but I have not, the things I used here is enough for actually doing real world stuff. So one example is a paper, Journey to an RTE3X509 parser. The code is available on GitHub. It do a full, realistic X509 parser for certificates. Because we know OpenSSL and the browser and so on have had lots of bugs in that code. But here we have one that actually is RT-free. It doesn't have any memory problems. It actually verifies a little bit more than necessary that some of the error codes are correct and that kind of thing. But that can be an interesting thing to look at if you want to know more about this. Also, there is a really good tutorial, Introduction to C Program Proof with FrameIC and its VP plugin that goes through what I have said in much more detail, plus much more information. I think that concludes my talk.
Wouldn't it be easier to just write it in Rust?
Well, that is an option. So you need to, as all technical details, you need to look at what you want to accomplish and what is cost and everything like that. So,
but for existing code bases, like large projects, do you like the effort required to annotate versus the effort required to rewrite? How do you think they balance?
I have essentially only verified things I wrote myself. And I write code in a way that are relatively easy to prove. So if you write sufficiently messy code, it is impossible to prove in this way. If you have written well thought out code that actually structures your loop as invariants and that kind of thing, it's more or less mechanical to actually do the translation. So if you look at the paper, for example, they wrote a new parser from scratch and then proved it. But since they wrote it from scratch, they sort of thought about probability to begin with, but they have never used this tool before. And they say that the time to prove it was a third of the full project time. But if you read what they say, they actually spent quite a lot of things doing unproductive things with the tool and trying to understand how it works and that kind of thing. And there are also things that are sort of impossible to handle. Let's say you have something that allocates a lot of memory, places in different data structures all over the place and so on, and you want to ensure that you not have stale pointers when you free something. That is really hard doing like this. There are sort of ways that in theory can be used, but probably not in. So if you write a browser, I don't think your JavaScript engine would be easy to prove in any way.
Yeah. I think this is a super cool kind of tool and idea. And it's also something I have tried to learn sometimes to use, but it's a challenge. But in some ways, I see this as a very similar approach to how Rust proves some things, because in Rust you have some of these annotations you have, and you prove some of the things you prove with the type system by having. So Rust defines many different pointer types, and each pointer type corresponds to one of the annotations you wrote. At least that's how I think about Rust.
Yeah,
I think it's a super cool way of approaching these kind of things.
Yeah, yes, I agree with also that there are big similarities in approaches.
The solution you have provided here is that you are having rules that is something that should be a constant declaration of the contract. So if you do this type of things, you don't fix the code. You just sort of add rules that is sort of giving approval to do things that should be done, change it in a C code. Any thoughts about that type of problem? You should really fix the code and do a const declaration if you don't do any changes in the data. This will generate better code.
Const in C is in many ways more a hint, because
Yeah, it's up to the implementation, but sort of it would be a better way to do the declaration that it doesn't do any changes. It would be easier for the C code reader to have
Yeah,
that.
right. On the other hand, you still need to prove it because the function
No,
could cast the pointer.
The verification prover should use that information that, okay, this is something that the code generator will not mess up with, and you don't have to add extra rules for it.
But the function may cast the pointer. It may be done implicitly if you have a big code base. So in this case, this particular case, yes, but it doesn't solve any work for the prover in a real code base.
Yeah.
There are ways you could do this by, that's actually one tool I'm working on.
I mean, can you have the rule generating using that information to have that assumption for the automatic
Right,
generating?
and as I said, if you want to do a really useful tool, there are lots of automatic things it could add. So if you use the language Daphne, for example, that is language used for formal verification, half of these annotations will be unnecessary because it can figure it out itself. So it's partly because FrameAC is trying to do the minimal thing itself.
I saw what looked like a target-specific limitation, the maxing thing there, to the power of 32 minus 1. Sorry. Yeah.
Yeah.
Is that because it's reasoning about the minimum size of the type, or is that something you put in?
No, it was a tool that actually expanded the maxint.
Okay.
So
Is it your maxint on the system you installed, FrameAC?
is this the system's maxint?
Okay.
Or rather, the tool has wrapper include files that have added lots of annotation.
Okay.
But you say we target your targeting. So if I had said that I would do the analysis for a 32-bit x86, then I would have other constants.
Okay, so you put that in. Okay. Thank you.
How does this differ from your Python tool that you used in your blog posts?
Right. So to the background, one tool I'm working at is taking the GCC internal representation, translating to sort of formal logic, and doing various analysis on that. So what I'm doing now is for each optimization pass, I take the IR before and after each optimization pass and verifies that they are equivalent. That is, if they are not, the compiler has introduced a bug. I also do the same with assembly for risk 5 to ensure that the backend has not changed the semantics. So my tool is adding infrastructure for doing this kind of thing, and I plan to try to prototype some types of tools for GCC that do this kind of analysis. So this could in principle be added in the GCC static analyzer, because you have lots of annotations you put on functions. You can say that it's non-null. You can say various things that are interesting. So one tool that I plan to release soon will use that kind of things to give you all cases where you have undefined behavior in your function as long as you have a contract with that. So if you have my prototype tool, plugin 3 does sort of that, but it's too limited to actually be useful. But
it's similar without the tedious work of annotation.
You need to tell the contract in some way. But again, often you do that by attribute non-null and so on. So the idea I have is try to not requiring full contract, only try to focus on the things that actually have been added. But it's hard to getting something that is both useful and not hide all problems. So I'm not sure if it's possible, but we'll see.
Thanks a lot.
Thank you.